Great. It seems like that works better. So good. Like I said, welcome to our third class on whole building design and energy analysis. For those who missed our first section, since I wasn't here last week, I'm Rob Best. I'm the Project and Education Director for Engineers for a Sustainable World. And just to let you know in advance, we're going to try and maybe a couple minutes early today. So I'll try to keep this brief. For those who hopefully saw my note yesterday, my email, I hope you got something that you can maybe draw or sketch with, because our activity today is going to be a little bit more hands-on and not so much digital research and digital data recording. So let's dive right in here. And I first just want to share a picture of what we're going to be talking about today. So Karen did a fantastic job last week of sharing with us how we deal with existing buildings and retrofits. And today we're going to be talking about brand new buildings. And it's a really exciting topic. It's one of my favorite topics because we get a whole lot of opportunity to do some really cool new designs and use some very cool new technology. So just as a reminder of where we're coming from, I always like to start with sort of the definition of, one of the definitions of sustainability, since that's ultimately what we're going after here. Energy efficiency is great in and of itself, but the reason we do it is because we're trying to meet our needs and hopefully not compromise the needs of the future. So energy, as we've talked about, is a big part of that. And in the context of buildings, that's a really important metric because we really want our buildings to last. And that's why we put so much effort, as Karen discussed last week, into retrofits. So here you may recognize some of these structures here, Notre Dame in the upper right, the Empire State Building in the upper left. And just to give you a sense of perspective, all of the buildings on this slide, the Empire State Building is by far the youngest at only 84 years old now. I believe I'm 1 year out of date on this slide. Some of our buildings have lasted over 1,000 years, so it's really important when we design new that we get it right and we get it right the first time. So the good news, Karen talked a lot last week about how we deal with buildings that are maybe not performing so well. But the good news is that we've gotten a whole lot better in how we design buildings. So all of those issues that Karen talked about last week, we're now getting better and better and better at designing buildings so that they're using less energy, so that we don't have those same issues and have to go back and fix them later. And the fact is, we've moved towards newer and newer buildings. Our rules and regulations around building codes have gotten much, much stricter, moving towards some of the standards that we've mentioned over the last couple of weeks: passive house standards, net zero energy buildings, and some others. So today we're going to talk a little bit about how we try and achieve that, or what it means to do this in the context of a new building. And this is really different from a retrofit building because we have a whole lot more that we can change, a whole lot more that we can actually do. Apologies again for the traffic noises behind me here. We have a whole lot more that we can do and a whole lot more that we can change when we start from the beginning. So we want to start by talking about design principles. And we're going to focus a lot today on the design of the building and not so much on specific technologies, because actually the main things that will affect the energy performance of buildings are definitely the design. In fact, if we do it right and we do it from the beginning, many of the barriers that we hear talked about as energy efficient buildings, those just don't actually exist. So if you've ever heard somebody say, well, it's too expensive, well, they're really probably just not starting from the very beginning. And as we go through, if you have any questions, if you have anything that you want to stop and ask about, please do stop and ask me. I'm happy to answer questions as I go along here. So, as I've already started to talk about, green design has to be an integral aspect of any new building. Energy efficiency has to be built in from day one, and the whole project team needs to be on board with how to go about achieving that. If we're all on the same page as that, then we can use some of the strategies, the design strategies that we're going to talk about now. The biggest thing that we can do when we talk about new design is to start by reducing the amount of energy through what we call passive strategies. And passive strategies we'll talk about mostly revolve around the orientation of the building, how we allow heating and cooling to actually take place, and where we allow lighting and different energy to come from the outside of the building and into it. And if that's a little bit abstract at this point, I will get much more specific, I promise. Once we've done those passive strategies, so once we focus on reducing that load, then what we're going to try and do is go into improving the energy system, and that's a whole lot of the cool high-tech options that perhaps you've read about or heard about, things like heat pumps, things like energy recovery chillers. I'll touch on those a little bit at the end. And then kind of the last thing that we want to do is renewable energy. So solar, batteries, those get a whole lot of play in the media. They're very sexy, for lack of a better word, but they're really the last strategy that we want to deploy. And there are a whole lot of reasons for that. If you remember in week 1, I asked the question of, well, why should we care about energy efficiency if we're moving to a renewable future? And so cost and some of the material impacts are a big reason why. So this chart that I've shown here, this is from a really good design firm known as Erin, and this is their sort of pathway to net zero energy buildings. And next week we've got 2 great speakers coming in. One of them is an expert in net zero energy buildings, and so hopefully he's going to talk to us a little bit more about what this pathway actually looks like. So diving straight in, what do I mean when I say it starts with the design, and how do we go about actually implementing some of these passive strategies? Well, some of the single biggest thing that we can do is think about how we orient the building. And that's not just thinking about what side faces north, although that is important, and south and east and west, but also how we orient with the landscape and with the wind, some of the other predominant features of our site. And again, we'll talk more about that in a minute here. Once we've gone through the orientation, we want to focus on reducing the energy load. So again, once we know how our site affects the building, thinking about things like where the wind's coming from, where we can get natural lighting into the building, and then even how people are going to use it. Once we know how people are going to use the building, we have a much better sense of how we can reduce the load. Passive energy gain and ventilation, that goes back to some of those orientation issues again with lighting, with wind coming through the building. And then as I mentioned on the last slide, we'll get into efficient systems, energy recovery, and renewable energy generation. So I'm going to pause here and ask, are there any questions about that sort of overview? That's the high-level introductory section, and we're about to go into specifics of how we implement these different aspects of passive design. So before I do that, are there any questions, any comments? Okay. Seeing none, and oh, we do have a hand up. Maya, do you have a microphone, Maya? I'm going to try to unmute you here and see if...
Do I have a microphone?
Yeah, you are unmuted. I can hear you.
Excellent. Okay. My question was this is all about new buildings, right? But most buildings aren't new, and it's not so great to just tear them all down and build new ones, right?
That is very true. And so the energy impact and the embodied carbon and embodied energy of new buildings does tend to be very high, especially because concrete and steel are 2 predominant building materials for most new construction, except for single-family homes. Those are both really energy and carbon intensive. That said, because of sort of natural structural degradation, changes in building codes and things like safety for earthquake zones, hurricane areas, and just natural turnover, we do expect to see about 25% of the building stock be rebuilt over the next 30 years. So that's a pretty substantial number. And then we pair that with the fact that there are a lot of newly industrializing economies, and especially in places like Shanghai in China, which is growing at a huge rate, Jakarta in Indonesia, some cities like that, where we're experiencing a whole lot of new construction. It's really important to understand both aspects of it. So I mean, that's a really great point. I'm certainly not advocating let's go tear everything down and start from scratch. But it is definitely good to keep in mind. Anything else there before we keep moving on? All right, well then let's jump into some of our strategies here of passive design. So as I already alluded to, the things that we really want to keep in mind when we talk about orientation are sun, wind, and even terrain, even what's around the building in terms of can we use some of the earth as insulation for the building itself. And going back to the question you just asked, Maya, this is one of the best ways to avoid some of that embodied energy and embodied carbon. If there are natural features of the site that we can utilize, even things like trees and landscape vegetation will provide a large benefit to the building. So if we take better advantage of those early on, then we can avoid some of those added materials into the new construction later on. So starting with the solar orientation of the building, the biggest thing that we're focusing on when we talk about orienting with the sun is how light and heat are going to get into or stay out of our building. And it's a little bit of a subtle point that's not always remembered or not always known, but the quality of light and the quality of sunlight for every different cardinal direction is really, really different. So when we talk about in the northern hemisphere orienting with the sun, the biggest thing to remember is that the sun is throughout most of the year in the southern half of the sky. And that's the thing that we probably all recognize at different points, but as a building designer, it's really key because that's where the majority of the heat's going to come from and also where the majority of the light's going to come from. The other thing to think about is east and west, and specifically in the east, that's when the sun rises, we have a much softer light. It's great for illuminating spaces, and it doesn't add so much heat for a lot of different reasons. But by the time we get to the west, yeah, we still have that light, but it's a much harsher light. There's a lot more heat that comes into the building as a result, and it also provides a lot more glare. So just from a comfort, an occupant comfort point of view, it may be great to bring that light in. We may say, well, that reduces our energy consumption, but at the same time, it less comfortable for the occupant. The last thing about the sun is photovoltaics. So I said renewable energy is the last thing that we want to consider for a building, and that's absolutely true. But at the same time, we have to think about it early on, because if we want to orient for solar panels, if we're going to be going for, say, a net zero target, we need to know early on how we're going to orient the building so that we have good exposure for photovoltaics. So think about how the roof gets designed, think about how it faces that southern aspect of the sun so we can get the most energy we possibly can out of it. So after we've kind of dealt with the sun, the next thing that we want to focus on is where is the wind coming from? So we've already kind of decided which aspect of our building is going to face south, how much light we're going to allow in, how much heat we're going to try and keep out. And then the next thing is to think about, okay, so where is the wind actually coming from? The reason we care about that is for heating and cooling. Wind tends to be, especially in warmer climates, a really great way to do passive cooling and passive ventilation. Most buildings that we've built in the last 30 years use a very active cooling strategy, which is for commercial buildings one of the most energy-intensive end uses that exist. So the more that we can use natural ventilation and natural wind, the more we can reduce that energy. And a cool fact about natural ventilation is that even at higher temperatures, just the fact that wind is moving through the space actually makes the occupants feel a lot cooler. So when we're talking about metrics, most people focus on the temperature of the space, and the temperature of the space being, say, between 72 and 76 degrees Fahrenheit for a commercial building. In actuality, if we just turn up the volume of wind that goes through and the speed that it goes through a space, people will feel a lot more comfortable even if the temperature is up around 80. So wind is a really important to pay attention to. Oops, I somehow have my slides a little bit out of order here. So let me jump forward to this one here. And the way that we tend to design with wind is by looking at this tool here. This is called a windrose plot, and what it tells us is how the wind flows across a site, basically where it's coming from, which direction, what month, and what frequency. So we can look at these charts for every month of the year and understand better how we can use that wind in our design. So let me jump back now really quickly, because what I meant to share, what I wanted to share too, was the equivalent tool that we use for sun. So we talked a little bit about wind and how we design with the wind and the tools that we use. The equivalent tool, the windrows diagram, when we think about solar aspect, is this, and it's the sun path diagram. And what this does is for any given latitude, any given location, it tells us where we expect to find the sun during the year. So what angle is it in the sky? How high is it? And that will tell us a lot of things about how much light and heat are going to get into the building. It also allows us to design with shading in mind. So as I said, the southern aspect gets a lot of sun, so therefore it gets a lot of light, which might be a positive thing. It also means we get a lot of heat. So one way we can avoid that is with properly designed shading. So we take that sun path diagram and we look at, okay, where is the sun actually in the sky? Where is it in the winter when maybe I want that heat in the building? And where is it in the summer when I don't want so much heat? And we can think about how we design shades, design the length and the depth of those shades to make the biggest difference. Distinct from shades and not shown on my slide here are fins, which typically run in a vertical orientation instead of horizontal, so that we can design to block, say, some of that western light that we don't want providing the glare. One cool way we can use a sun path diagram to sort of look at some of those more natural aspects and maybe provide shading for us without us even having to build shades is to overlay it onto site images. So this is actually from a project that I worked on here in California, where we went out and we took images of the site and we overlaid it with that sun path diagram to get a sense of how much the trees were actually going to block any sort of photovoltaics we might install, and also any sort of windows, so that we didn't have to provide shading. Okay, so now the last thing that we want to think about from site orientation is the terrain. And for most sites, this doesn't matter as much. For most sites, especially in cities, we're building on flat ground. We're building in a place where there's not maybe a berm or maybe hills or water that we can take advantage of. But in places where we do have some interesting terrain, that can really provide some strong benefits for our building without even having to go into, as I said before, added materials. Earth is perhaps one of the greatest insulators that's out there. So as shown in this diagram, we can do some really, or so this image, some really interesting things with varying structures. But think about then there are trade-offs with perhaps providing light. So in some climates this makes sense, in others it wouldn't. In areas where we may have a body of water nearby, a lake or an ocean, that can provide us some free cooling. And we can think about how we might want to orient the building, not just to provide a nice view, but to take the breeze and the cooler air that comes off of that water and bring it directly into the building. Especially with ground, we get a lot of benefit though, and ground temperature tends to stay pretty constant throughout the year. It may go up and down, but certainly not as much as air temperature. So it provides us with a really nice heat source or heat sink that helps insulate the building a lot throughout the year. It basically will reduce your heating and cooling loads by 30 to 50% or more in some cases. So definitely something to keep in mind if the site allows for it. And so this is now we're kind of coming to the close of the orientation discussion. And so one thing that I always like to remind at this point is don't forget about the people who use the building. Because at the end of the day, it's great to design with the sun, it's great to design with wind, it's great to design with the ground if we can. But if we don't think about how people are actually going to use this space, and we only focus on energy, we're going to run into a whole lot of issues. And to Maya's point, if we build a brand new building and nobody likes it, and we have to tear it back down, what have we actually just done with the property itself? Okay, so at this point I want to pause again and ask, kind of going through that orientation, that first aspect of passive design, do we have any questions now? Feel free, if you have a question, I might to raise your hand or just to type it into the box, and I will gladly answer. All right, I don't see any questions, so let's just keep going then. One more aspect to consider, not just the architecture, not just the visual aspect or how people use the building, but the economics. So curb appeal, market appeal, colors, materials, and landscaping. And this gets a lot more, this is no longer so much of the site consideration, but a lot more of the material conversion. And so as we move to talking a little bit more about the technology, the appliances, materials, this is something to overlay on top of our entire conversation and our entire discussion is how are we going to actually sell the property? How are we going to allow people to use it? So thinking about materials, once we've done our best with orientation and done our best with the passive aspects of the design, the next thing we want to do is think about how much heating and cooling the building will actually need and will actually use. And so we're all engineers here. I hope maybe you've been exposed to heat transfer at some point. If not, this here is a little bit of a primer on heat transfer and what to expect or how heat transfer in walls actually works. So we consider typically the wall sandwich is what we refer to it as being all of the materials that go into the wall. And that whole composition has what we call an R value, which is a thermal resistance, if you're unfamiliar with that. It's exactly analogous to an electrical resistance, and it basically says, well, how much heat is going to pass through from the outside of the wall to the inside of the wall, or vice versa. So as you can see on this diagram here, we have sort of one R value for the convective heat transfer of air against the outside of the wall, different R values for, in this case, the glass and the inner part of the glass. In this case, we're looking at a window. And then again, another R value for the inside air and the convective heat transfer there. So if we add all of those in series, just like we would considering an electrical system, we get the overall R value for the wall. And that tells us how well performing our wall actually will be at keeping heating and cooling on the sides that we want it for different parts of the year. If you grew up in a single house with a little yard, you know, the American suburban dream, you probably had a house that was built out of wood. Most houses in this country are built out of wood framing. Some have insulation, not all do. And Karen talked last week about how we can test the thermal performance of some of our buildings and adding insulation in places where we don't have it. Typically, stud frame walls with insulation are about R11. In some places, they can be up to R30. So that R value, again, is a measure of the thermal resistance. It's the inverse of the watts per meter squared Kelvin, which would be the U value or the conductivity value. R30 tends to be a really good resistance value in the Northeast and in colder climates. If you're out here in California where I live, R11 tends to be pretty standard and pretty good. Now, the biggest thing, though, that loses energy for us is actually our windows. And Karen may have touched on this last week as well, but our windows tend to be R1, at best maybe R5. So at best, they're half as good as our walls. At worst, they're 10, 15 times worse than our walls. And so that's a big issue because, as we talked about before, with passive strategies, we like windows. They let sun in, they let wind in, but they let heating and cooling out. So there's a lot of balances here. And when we talk about energy efficient design, there are always trade-offs and always balances. So one of the things that we need to think about, and I keep coming back to your point, Maya, because it was such a great one about the embodied energy and embodied carbon that's present in buildings and the impact that has. We have a lot of choices when we think about insulation for buildings and for walls. And so here are some of the most common things that we use to insulate buildings, with ranging from the artificial and, well, artificial meaning chemically manufactured based on actually oil in a lot of cases, polystyrene, polyisocyanurate, and going to some more natural materials, cellulose and rock wool. And at the bottom, I've got 3 different windows just to show you. You may be familiar with single pane, double pane, and triple pane windows. The different efficiency levels that we get from those. So there's a big variation in what we actually can do in terms of insulating the building. And we need to think carefully about how much we want to spend and what the right balance is for the climate that we're in. It's not always true that more insulation is better. So I already touched on this with the trade-offs that we have in windows. One of the tools that we can use to help us balance the right amount of window in a space is this here. And this is a radiance an image from a radiance simulation. What this does is it traces for different times in the year how much sun is coming through the windows and what that actually does on the inside of the space. So this is a house project that I worked on, and we did some simulations here with a software called AGI 32 and also some software called Radiance. And that allows us to get these images here where we can see how does the space actually look with only natural lighting. Again, think about our trade-off between thermal and light. We have some ways here now of actually quantifying and assessing early on, and then projecting that back to the potential users of this space to say, does this look good, does this feel good to you? The other trick that we can use in new buildings, and this is being used more and more, is thermal mass. And thermal mass, as opposed to trying to keep heat out or cooling out, actually works in the opposite. In this case, we want to invite it in at certain times of the day and store it. So concrete and stone are two of our best ways of projecting heat and cooling back into a space after we've stored it overnight or during the day. And thermal mass really works by absorbing that heat and then re-radiating it at times when the space gets colder. It's a great strategy, especially if you couple it with passive ventilation and can bring in air at the right times of day to help heat and cool the space. As I mentioned, concrete and stone are two of the most traditional ways to do this, but there's some really cool new products out on the market that you could look into if you're interested in this, that use either natural waxes or engineered waxes that will melt at exactly the temperature that we would like in our building, so right in that 72 to 76 Fahrenheit range. And so what those do is they absorb heat during the day and melt, and that helps stabilize the temperature. And then as they solidify, when the temperature drops, they're re-radiating that heat back into the space. They're very thin materials. They're much cheaper and much less heavy than traditional stone and concrete. Work almost as well within the space itself. The other common material that we've been using for about 40 years now is water. Water has a very high specific heat, and so in what we call a trome wall can be really effective in balancing the temperature of the space. A trome wall is really just concrete blocks or plastic blocks containing a bunch of water, and we use that then right on the outside of the building to absorb and re-radiate some of that heat. So thinking now no longer about the inside of the walls, but thinking about the outside of the walls themselves, there are some tricks that we can employ to either bring in or reflect heat outside of the building itself. So one of the most common things that we want to do is think about how, if we're in, say, a hot climate like Southern California, we don't want that heat getting inside. So one of the things that we can do is use some high reflectivity materials, as simple as white paint, or as more complex as some new polymers that help prevent even larger swaths of the infrared spectrum from getting into the building. And then finally, as I've already mentioned a couple times, landscaping is one of our biggest tricks, one of our best aspects for helping regulate the temperature. Trees, buildings, trees, bushes, lakes, streams, other sorts of natural features can really help us regulate the heating and cooling. I see a note here that, Troy, you have a question. Trying to read it here. So Troy asks, can I speak to the gas-filled double-paned or triple-paned windows and weigh that R value increase against its environmental impacts, and let's see, and whether making those windows thicker is a good sustainability return on investment. That's a really interesting question, Troy, and I think it's really climate dependent. As I said with insulation, depending on where you are in the country, there is such a thing as too much insulation, and by the same token, there is such a thing as too good of a window, if that makes sense. You certainly don't need in California, for instance, a triple-paned argon-filled window, and in some cases, I'm not entirely sure the impacts of, say, producing those inert gases and what that gives you in sort of a sustainability ROI perspective. But I do know that there does come a point where adding more insulation really doesn't do a whole lot for you from an energy perspective, and so the added materials and the added costs really don't necessarily pan out. Good question, though. And again, coming back to the fact that there are trade-offs right and left in buildings, this is just another one of them that we have to consider. So to kind of close out this section on materials and thermal impacts, the last thing that I would share is when you're designing, just really keep in mind how heat moves. And Karen talked a little bit last week about identifying heat sinks and heat sources or points of infiltration within your building. Just keeping in mind how heat's going to flow through a space will get you much, much farther than we even were in designing buildings 30 years ago. Because honestly, this may seem very basic, but 30 years ago, we did not consider any of these aspects at all. So Karen talked about some of these things last week in her discussion of retrofitting, but heat loss, especially in roof areas and attics, if we think about specifically single-family houses, is huge. Infiltration and losing conditioned air into unconditioned spaces is one of our biggest losses. And when we design buildings for the first time, we have a chance to make all this right up front. The other big driver of this is humidity. It takes a lot more energy to deal with humidity and humidity getting into a space. Apologies for the motorcycle. It does to just heat or cool dry air. So the more infiltration that we have, the more likely it is that we're going to have to be dealing with humidity, and that's going to cost us a lot more in terms of energy. I put this in here just to remind you. I know that Karen sent out that wonderful wrap video about the blower door test and how we check for infiltration and loss in a building. It's something that we do need to consider in new construction as well. What's the infiltration rate, and what is a good infiltration rate? So as I put here, old houses typically a 0.5 to 1 air change per hour, which is a lot of infiltration. New buildings, new houses, we want to get around 0.3 or even down below 0.1, depending on the standard that we're shooting for. And I know I've harped on this a lot, but thinking about architecture and heat loss, there is a big, big trade-off between a lot of the things that we've discussed. Bringing energy, bringing light into the building, bringing heat into the building, and then losing some of those resources if we're not careful about how we use them. So we are now about halfway into our time here. And I will pause again here and ask, are there any questions at this point? I've gone through a lot. I've gone through a lot quickly. I could spend a lot more time on any one of these aspects. But there are a few more things that we want to talk about today. So please do ask me questions if there are confusing points and how quickly I've gone through this. Okay, so then I hope, as I said at the beginning, you guys all brought something to draw or write with, because it's time to do our in-class activity. And I did not make slides for this because we're not using any sort of slides today. So what I would like you guys to do is keeping in mind some of the stuff that we just talked about, orientation and about designing of buildings. We're going to keep it to something simple and think about a single-family house a little bit here. And what I'd like you to do is sketch out kind of what you think your ideal house might look like. That can be as small or as big as you want. And think about a lot of these different things. Think about the orientation. Think about where you might put windows, where you might not put windows, how you might treat wind coming into the space. Sketch that out, and what I would like you to do is with me via email or via, take a picture and send me an email, take a picture and put it on the Google Slides. For the pre-class activity of different buildings, different technologies, was able to do that. So those slides are here online. I know I just said I didn't make slides for these, but since nobody seems to have shared anything from the looking at commercial buildings in their area, we can just reuse these slides. So spend a few minutes. You can sketch directly in this. You can put a picture, or you can just note some bullet points down. Let me get this this link for you here. And let me see if I can share that by chat. Okay, you should in the chat box have a link to the slides that I'm showing on the screen. So spend a couple minutes, get something out, either on your own paper or on this online resource, and then perhaps if you can add a picture of it straight to these slides. If you cannot, if that's a little bit more difficult, if you might maybe make a couple of bullet points, and then I would really appreciate if you could send me an email later, send me something after the fact with an image of whatever you thought about. If you don't have access to pen and paper, take a look, maybe dig around a little bit online and see if you can find an image of a home and comment on some of its features, whether it's you think it's a good design or a bad design based on some of the things that we've talked about. So I see a couple of examples in the slides here of pictures that people have found. I really like the solar picture here, Aaron, that you've dropped in. That's a very cool design. All right, take about 2 more minutes here to work on your own sketches or add some things into the Google Slides. If you don't have time to add your own drawings in, try and do that after the class here, because we will revisit this at the beginning of next week's class just for a moment to take a look at what people came up with. Whoever's showing the Redondo Beach House, that's really cool. It looks like that's shipping containers. Is that what I'm seeing there? It's a very cool reuse of materials or so. All right, let's take about another minute here just to finish up whatever you're working on, and then we'll bring it back and go through a couple more things before we wrap up here today. Grace, I love the sketch here of a grass roof, which is not something we even really talked about, but a great way of preventing heating and cooling by using a very natural material. Thinking back to some of the trade-offs we talked about, one of the really interesting things there is now we don't have as much room for PV, and I see that you've managed to fit some on your roof there, which is awesome. But that's definitely a trade-off that we have to make, especially as we get to taller buildings where there's less roof area per building area. So very cool design. I'm really enjoying it. All right, so in the interest of time here, guys, let's bring it back, and let's go through a couple more things that I wanted to share. If you do have other sketches or images, please do feel free to share those later on the slides. But let's go ahead now and talk a little bit more. We've gone through, I spent most of the time intentionally on passive design strategies and material choices for insulation and thermal mass. And after we've done that, we're 90% of the way there, but the last 10% is still a very important 10%. And that's what we call the active systems. It's how do we actually now, with the little energy, hopefully, that we're using in the building, make sure that we're using it as efficiently as possible. So the biggest user in commercial buildings is lighting and heating and cooling. Karen talked about that in week 1. And in residential buildings, it's typically heating, and then, again, either cooling number 2 and lighting number 3, or depending on where you are in the world, those could be in a slightly different order. So one of the most important things we can do is think about our HVAC strategies. Think about, can we use low-energy heating, ventilation, and air conditioning? As we talked about earlier today, the ground is actually a really nice heat source and heat sink, so maybe we can actually use that through a geothermal heat pump to do heating and cooling. The other thing that we can think about is all of the different end uses in a building. Can we use lower energy appliances, lower energy lighting? And then finally getting into smart controls and smart feedback. And I intentionally put that last because we run into an issue with smart controllers about people's willingness to use them or be in buildings that use them. We don't necessarily want to design the human out. We want to design with the human who's using the building. And sometimes we can fall into a trap with smart controls where we're just designing as if nobody is going to be touching anything. And trust me, that never actually works as well as we think it should. So just going back to the home for a second, since you guys were just thinking about that, where energy is used in the home is all over the place, and sometimes it's more than you might think. So here for our oven and our microwave, 5,000 and 1,500 watts respectively. That's a lot of energy that we're using. Now, luckily, we don't constantly run those two appliances, I hope, but one of those things that we want to be aware of is where all the energy is used, all of those different possible end uses, and when it's being used. And that last part is really important when we get into modeling energy consumption, which we'll talk about a little bit at the end here, and which hopefully you'll get to explore a little bit more over the next week. Just another way of representing how much electricity appliances in the home use. You see there are some water heating especially that use a ton of energy compared to some of our smaller appliances. And so you hear a lot about getting more efficient laptops or more efficient washers, dryers, and those are very important, but we do want to keep in mind also where our biggest consumers are and where we can perhaps make the most savings depending on how much money we have to spend. Transitioning from residential to commercial buildings, as I said earlier, cooling and lighting tend to be our biggest consumption in commercial buildings. And those things tend to be larger. What we do is we consider zones of occupancy. So rather than thinking about how we heat and cool or use energy in the entire building at once, we break it up into different areas. So areas near the outside of the building we typically refer to as perimeter zones, and that's where we really focus on bringing in natural lighting, heating, cooling. At the core, that's typically where there's a lot of heat being generated from things like copy machines or printers, just really heavy consumption. And those areas are where we require a lot of cooling and need to pay attention. But again, the same strategies apply to a commercial building in terms of thinking about where that energy is being used, how much it's costing us, and making smart choices about how we reduce that. I wanted to give a couple of examples because a lot of the diagrams I showed earlier were for residential buildings. And so this is an example of a commercial building. Actually, it's an educational space. It's that same building at Stanford that I showed in week 1. How the orientation was taken into account in terms of looking at, you see here, where sun at different times of the year, those more direct overhead rays are summer, and the blue rays, the sort of more slanted ones, are the winter sun. So here we can really take into account how that light and energy gets into or does not get into the building. Similarly, a lot more commercial buildings these days have shades on the outside of them. It's not something that we used to see. If you look at, say, towers that were built 30 years ago, it just is a wall of glass on the outside. It's a curtain wall is what we call it. And now we're starting to think about how we shade those curtain walls as well. It's a big energy saver for the perimeter zones of a commercial building. And then again, going back to that building at Stanford, thermal mass. You can do it in a commercial building just as well as you can in a residential building. Here, all of the floors are concrete, so that provides a lot of thermal mass throughout the space. In fact, you may even have a greater opportunity to do it in a commercial building than in a residential building, just because you have more space and you can store more heat. So one of the things on the technology side, some of the cool new strategies that we're really starting to deploy, especially in commercial buildings, are combined strategies of heat pumps, which, if you haven't yet taken a thermodynamics class, heat pumps are exactly like refrigerators, just in reverse. We physically use electricity to move heat from a colder place to where we want it to be, to where we want it to be warmer. It turns out to be a really energy-efficient way of heating a space rather than, say, burning gas or just heating up a resistor really hot and letting it radiate. So it's a really efficient way of doing space heating and water heating, and so you see a lot more buildings using that technology today. The other thing that we do is once we've spent all that energy to heat and cool a space, we don't want to just exhaust it back to the environment. So heat recovery ventilators and energy recovery ventilators, or also known as economizers, as we exhaust air from the building, because it's at that point perhaps been already through the space and we want to bring in fresh air, before we let it leave the building, we put it through a heat exchanger so that any conditioning that we've done to that gets passed into the incoming air for ventilation. Again, a simple strategy 30 years ago, not something that we ever did in new buildings. And then the last thing, and this is perhaps the biggest one that we've done, that's starting to gain much more traction, even in really cold places, is not using as hot of hot water or as cold of cold water to heat and cool buildings. So for years in the commercial space, we've used 42-degree Fahrenheit chilled water and blew air over that to make air conditioning, and we used 180-degree hot water or steam in order to do heating. More recently, we've been thinking about combining heat pumps with essentially a 60-degree reservoir, so more or less the same temperature as the ground, which is why geothermal resources make a great deal of sense. And that just means we don't have to heat or cool that water as much, and that's a huge energy saver. This is especially important as we get into thinking about how we connect buildings together. So beyond just the scale of a single building, we can more efficiently make hot water, cold water, or this tempered chilled water at about 60 Fahrenheit by thinking about all the buildings together and centralizing that heating and cooling infrastructure. So just if you're interested in this, there's a lot of good research on district energy systems, and I encourage you to take a look. It's also where my doctoral research fits in, so I'm happy to discuss this more at another time with whoever's interested. So in the last 5 minutes here, the last thing that I want to talk about, and this is the lead into the exercise that you guys are going to do over the next week, is how we model all of these different technologies. We've talked a lot about strategies, passive strategies, reducing some of the energy consumption in buildings. And the best thing that we can do at an early stage is to understand how these will actually play out as best we can. There are a lot of software tools out there, a lot of things that we can use. I've listed a few here for different techniques. I mentioned AGI 32 and Radiance earlier when I showed that picture of the house where we looked at lighting simulation. For energy, for full energy, we can think about things called programs called eQuest, EnergyPlus, or Autodesk software Revit that will help us do a whole building energy analysis. If we want to really dig into natural ventilation, those don't quite work so well, so we need something like a fluid dynamics model. And ComSol or Autodesk has another product out there as well. They do really well for analyzing those systems. This is kind of what they look like. We create these 3D representations of the buildings. In the upper left there is SketchUp, and in the bottom right is Autodesk's Revit. And with those, we can then simulate them in these different multi-physics or thermodynamic engines. We can also pass them through lighting models. So I showed you one image of that before. This is another way that we visualize lighting. And sometimes we even build physical models to take a look at, as we see on the left there, how the sun is going to affect the building through, that may look like a sun path diagram because that's essentially what it's meant to represent. Oops. So to dig into energy modeling just a little bit, because this is what your assignment is for the next week, Energy modeling has been around since the 70s only. So again, all these different active strategies, we didn't have a way of quantifying them effectively throughout an entire year until about 40 years ago. It wasn't part of the code in many states until 2000, or the early 2000s, when ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers, and certain states started saying you have to simulate buildings in order to get approved. Perhaps the leading model on the market today is a software called EnergyPlus, developed by the Department of Energy. It's a multi-physics simulation that uses heat transfer, it traces light rays, and it solves for every single space, for every single hour, what the heating and lighting conditions are in the building. It does simulation of internal loads really, really well, and it iterates between internal and external loads to make sure that everything is balanced inside, outside the building, inside the walls, so that you can guarantee as close as possible that the solution is good. Now, that said, it's really not a very easy software to use. They haven't developed a good interface for it, so you're essentially having to write new code every time. So instead, the software that I would like you guys to play with a little bit over the next week is called eQuest. And this is also a multi-physics simulation. It was the precursor to EnergyPlus, and it also does really good simulation of internal loads. The one challenge is it doesn't use an iterative solver, so it can have a greater amount of error. And we see this sometimes in how buildings are simulated and then constructed. Oops. So key differences between the two. EnergyPlus, definitely more accurate, but like I said, it's much harder to use. And then eQuest is simpler, it takes a lot less computation time, and it's widely used in industry. So it's one that you should familiarize yourself with if you're really interested in this space. Positive aspect for both of these is that they're free. You can download them online. If you just Google eQuest download, go straight to the page, EnergyPlus download, same exact thing. So I don't know why my screen is skipping ahead without me asking it to, but your assignment for the week, and this is where I'm going to wrap things up. We're going to have a little bit more to do this week since there wasn't an assignment coming into today, really. And also, we're switching up the schedule. So next week we have 2 guest speakers coming in, and then we're going to wrap up our 5th week with alternative building materials, just based on scheduling for our guests. So the assignment this week is to download eQuest and walk through the schematic design wizard, which is the easiest setup. Play around, make your own building, and then share your geometry and your output results in the same slides where we shared our residential buildings earlier. There's a link to all of this in the folder for the class. It's also on the syllabus. There are also 4 resources that you can use for learning eQuest, for understanding how that interface works and the different things that you can do with it. Also, in advance of next time, there are two videos that we want you to watch. Neither of them is very long. But just to familiarize yourself with some of the topics that we're going to be talking about next week. So that's it. That's all I've got. I apologize that we were a little bit rushed there at the end. I want to now pause one more time and ask, do we have any other questions, any other last things before everybody disperses for the evening here? All right, well, I don't see any last questions. So, I hope this has been interesting. I hope this has been informative. There's a whole lot in the world of energy modeling, so I encourage you to go play with eQuest, run through some of the tutorials if you've got the time in the resources that are shared in our folder. You can take a look at those. If I just jump back here really quickly, I'll show you what those look like. We can go back to our class folder here, and we've got eQuest Intro 1 through 4 that you can take a look at. The first one is some slides that I put together. 2, 3, and 4 are resources from other sites on the web, and there's some other great sources out there too. So please do play around with that. I hope that you enjoy it, and if you have any questions, run into any issues, feel free to send me an email. My email address is just rbest@eswusa.org, and I'll be happy to answer those throughout the week. So with that, thanks again for attending week 3, and we look forward to seeing you for our 2 guest speakers on commercial buildings, net zero energy commercial buildings, and passive house residential buildings next week.